Dr. Guho Dai and Dr. Jeff Ruberti. So my project concerns the 3D printing of type 1 collagen. There have been numerous sessions at BMES concerning this particular project, but my work is a little different in that I'm very concerned about the nanoscale and microscale level of my printed construct. Type 1 collagen is found in your body very commonly in tendons, in bones, in cornea, and in skin. It's the major load-bearing protein found in nature. So if you look here at this image, you can see that it's very structurally aligned. These individual fibrils are the collagen fibrils. This is in cornea. The hierarchical structural organization of collagen influences its functional properties. So effectively, structure equals function. This is very important because if we're trying to make something like a tendon or a cornea, you want to make sure that its structure from the nanoscale to the microscale all the way up to the macro scale is all near native. So my work is based on a previous paper from Jeff Ruberti's lab. What they showed was that pure extensional strain can be used to align high concentration monomeric collagen to a near native state, producing highly continuous fibers. However, the method that they used was harder. It's harder to make sure it's high throughput because what they're doing is they're pulling out these highly continuous fibers from a droplet using a glass needle. So my project is to scale up extensional flow-induced crystallization of concentrated collagen monomers to direct print these highly aligned structures. So my first step was to understand the structure of the nozzle I would be using to print. Because we want it to be constant extensional strain, it needs to be a hyperbolic nozzle. So if we look here, this is a beautiful representation of a hyperbolic structure. And to make this very particular hyperbolic structure, what I wanted to do was understand the relationship between the radius as it gets smaller and also the x as it goes down the length of the nozzle. So I generated an equation using two starting equations here. This is just the definition of extensional strain rate, and this is just conservation of flow. And I generated a formula using a couple of design specifications, 0.7 extensional strain rate. This comes from the previous paper, and 100 microliter per second cube. And I tested this constructed nozzle in a fluid dynamics software, ANSYS. And what I did was that I constructed my hyperbolic region, and I had a straight region here just to induce laminar flow. And what I found is with about 500 representative fluid particles, which have the viscosity similar to 50 mg per mil collagen, concentrated collagen, the velocity over the path length, the slope was around 0.7. So that can be approximated to be the extensional strain rate. So computationally speaking, this is a feasible project. However, we start getting onto the real world stuff. So the first thing to do was to concentrate my collagen. I use dialysis because it's a very gentle method, and it doesn't induce any sort of too many structural changes in the collagen, especially if I'm doing it to only 15 mg per mil. So this is an assay I use to detect my concentration. It's the hydroxyproline assay. These are figures of my standard curves. And the samples were calculated to be between 15 and 21 mg per mil. The next step was to determine the conditions under which the bioink polymerizes upon flow through the nozzle. We don't want it to polymerize before it flows through, and we also want to make sure it does polymerize right inside the nozzle. So what I calculated was I looked at time to polymerization using turbidity, so how cloudy the solution is. And at lower pHs, you can see here, it tends to not polymerize at all. It remains unpolymerized collagen via detection under the microplate reader. When you start getting to higher pHs and higher temperatures, it takes less time to polymerize. So what we figured out is that at room temperature, pH close to neutral, so physiological values, can be utilized before polymerization of the reservoir fluid occurs inside the device itself. So in conclusion, this is a testable prototype for 3D printed highly aligned monomeric collagen, and it's been scaled up from previous work. Currently current studies are ongoing. Firstly, I am testing flow analysis using 1.9 micron fluorescent microspheres to calculate the extensional strain through the nozzle, and also to determine what kind of flow profile is there, whether there's any kind of mixing or turbulence, which would definitely affect my final structure. I have constructed a prototype nozzle using 3D printing with Formlabs. And finally, the application of this project would be basically making collagenous substrates for repair and replacement of deteriorated tissues, such as injured or diseased tendon, cornea, and extracellular matrices. Thank you.
Thank you.